All right, so fortunately, you got one more test behind you. That is done. And then for our intro to circular motion, what you're going to catch in this unit is that objects traveling in a circle behave under the same principles, the same Newton's laws, as objects traveling in a straight line. The main difference is that there's going to be a few more things to think about. We're going to kind of layer on a little bit more information. It's still going to impact the energy the same way as before, but there's going to be a few new equations. It's going to impact the kinematics equations as well. There still will be some with velocity and acceleration, but they'll be just a bit different with objects that are moving in a circle instead of in a straight line. And so I want to start with a demo and show you just kind of an example. My hands are going to be full with this demo, so if you can let her when she comes back. I think she should be back briefly. But this is actually an experiment that we do. We won't have a chance to do it in this class. We're going to do some other activities, but this is one that we do in the AP class. And I thought at least show you the setup of it so you can kind of get an idea. And we might have you try it sometime just so you can kind of experience it yourself. We're going to do some different activities for our more hands-on stuff. But basically, the idea for them and what you can try out sometime if you want is I've got this stopper, this rubber stopper like from chemistry class. It's just a big one tied to one end of the string. And on the other end, I've got this pretty big weight, 500 grams, half a kilo, so about a little over a pound. And by spinning this stopper at the top at a certain speed, I can keep this from falling. The tension in the string that stopper is creating creates tension in this part of the string to keep it from falling. But if I slow down, then it starts to fall, okay? If I speed up, it starts to rise, okay? So I'm actually changing the force by adjusting the speed and the radius of that stopper that's traveling in a circle to generate more force. And the more force, the higher that goes, and the less force, the lower that goes. Make sure I have myself in the head. But that's just an example of something in circular motion. And the idea behind what we'll be learning is that for something to go in a circle, there has to be a force. Because if I just took the stopper and threw it, it would just go in a straight line, right? So for it to go in a circle, there has to be something making it go in a circle. Otherwise, it would just naturally travel straight. Objects normally go straight. If they're going in a circle, something has to be happening. And so in this case, and you can even start it from like nothing and spin it up. And by creating a force, I can make it go in a circle, okay? Otherwise, it wouldn't travel in a circle. So that force has a name. We call it centripetal force. So you might have heard of the word centrifugal before. Centrifugal force, we're going to talk about. I'll give you a spoiler alert, it doesn't exist. When we say that in common language, we're actually describing another physics phenomenon because centrifugal force isn't a thing. Or at least not a force. It is a thing, but it's not a force. We call it that mistakenly. But this is actually called centripetal force. And so that's an example. If you want to try that one of the days when we're doing some hands-on activities, you can do that. But I want to just give you kind of a quick demo. And then I've got a couple short videos to show you. The first one I've done in different settings, different aspects of this demo, but one of them doesn't work in this building for two reasons. The carpet, it's going to be rolling a ball on the floor, but the carpet slows it down too much. And two, I don't know if you guys know, but this whole building slopes like that. And because it's not a flat surface, that also makes it doesn't work. So I can't really demonstrate it easily, so we'll watch on the video. The other one is actually he uses a sparkler and a drill, which is pretty cool. And I've done it when I could get easy access to outside and easy access to sparklers, but I wasn't even sure where to find sparklers here in California. I've not really seen fireworks for sale here. It might be illegal. I don't know because of the fire hazard. You guys know? Okay. Again, in Indiana, they don't have like the fire risk and stuff like we have out here on the West Coast. So you could find fireworks stores and stuff and just go buy them, especially around 4th of July, but really all year you could find them. But I haven't really seen them here, even around 4th of July. You must have to go to a special place, I guess. So one, I didn't have access to them. Two, again, with the carpet, with sparks flying. I know this carpet's flammable because we had a little accident in my AP Physics 2 one day where they were trying to create convection currents with some things that were on fire, and one of the kids bumped the table and one fell off onto the carpet. So the carpet does burn. We found that out. So since it's not flame resistant, I didn't want to risk it, and I don't really have easy access to sparklers. So we'll show you the video instead. The other one's based on the International Space Station, and obviously we can't take a field trip to go there and try it ourselves. So it's just a way for you to see some of these principles in scenarios that we can't really either do at all, or at least not do safely here because of our circumstances. So the first one's pretty short, like 3 minutes. It's actually a video made for physics teachers. But I'm just going to show it to you since it's a little bit more difficult for us to demonstrate them in person. Is she here?
Oh, can I use that?
Oh, yeah. Hopefully I will. There we go. Just slow. First, a commercial from Grammarly, it looks like.
So I've got my essay written.
This is a great demonstration for showing that if something's moving in a circle and you remove the centripetal force.
We'll watch more, but I wanted to pause it here so you can see. You'll notice these sparks that are flying off. The sparkler obviously is attached to the drill, so the physical sparkler itself is traveling in a circle. But these sparks are flying off, and if you know a little bit from trig or geometry, they're flying off tangent to the circle. Okay, and that's one of the things we're going to learn about centripetal motion, is that when objects travel in a circle, if whatever force is making them do that vanishes, like if I were swinging that stopper and the string broke, the objects fly tangent to the circular path they were on. So you can actually see the sparks doing that in this demo.
It'll move in a straight line. But if you're teaching circular motion, I've got another demonstration that's worth doing first. This is a really simple way to introduce some basic ideas about circular motion. The ball moves in a horizontal plane, which makes it easier to understand the forces involved than with, say, something moving in a vertical circle, because we can ignore gravity. When I do this with my students, I place an object about there, and I ask them to tell me when I should lift the hoop so the ball knocks it down. Right, so as a physics teacher, I knew when to lift the hoop because I knew the ball would go off at a tangent. But that's not obvious to everyone, and this demonstration can really help to clear up misconceptions about things flying off radially when you remove the centripetal force. The ball goes from moving in a circle to moving in a straight line, and we know from Newton's first law that if something is moving in a straight line at a steady speed, the resultant force on it is zero. So what's going on when it's in the hoop? Well, the hoop exerts a contact force on the ball at right angles to its surface, and that force changes the velocity of the ball. The force is always directed towards the centre of the hoop, the centre of the circle. Take away that force and the ball obeys Newton's first law and carries on moving in a straight line. This is true of all objects moving at a steady speed in a circle. The instantaneous velocity is always at a tangent to the circle, and the force keeping it moving in a circle is at 90 degrees to this, that is, towards the centre of the circle. We describe the resultant force that makes something move in a circle as a centripetal force, and it's important to emphasise to students that this word simply tells us the direction of the force and nothing more. The force may come from a contact force, as in this example, or friction, or gravity, or tension in a string, or any combination of these forces, so it's really important to look carefully at any particular situation to identify the origin of the centripetal force. This is really just a more exciting version of the demonstration with the hoop and the ball, and it's not as dangerous as it looks. If you're going to do this in class, wear some goggles and a lab coat to protect your clothes from any stray sparks. Stand your students a couple of meters back in a plane that's parallel to the plane of rotation.
We don't have to hear all the safety explanations, but just wanted you to see the sparks flying off and how they go tangent. I have actually made a circle out of pool noodles over there and used like a pool ball or something like that, but the friction between the ball and the hoop and the friction between the ball and the ground slows it down too fast so you can't see it very well. And then because the whole building slopes this way, that affects the way the ball moves. So when I lift it, it curves downhill instead of going in a straight line because the building's not level. So I've tried it, but it just doesn't work great in this setting. All right, and then the other one, this is from NASA. One other thing I thought of when I was listening to him this time. Pause this first once it's ready. Have you guys ever, I think it's called a bolo. Some places in some countries they use them for hunting. It's like two weights on the end of a string and they spin it and then they throw it. Have you seen those before? Yeah. And it like wraps around the legs or something and catches the animal. So if you were doing something like that, when you would throw it, you don't want to throw it when it's in front of you because it's going that way. Like you don't want to let go of it when it's here because it's just going to take off that way. So you actually want to time it so that when it's coming around right here, that's when you're going to throw it so that it's going towards the direction you want. And you kind of naturally can feel it in your hand when you need to let go. Most people can. I've had some students try it. We used to get like rubber stoppers and go outside sometimes and just throw them and see who could hit a target. We might try that one day just for fun, but it's funny. Some students have a hard time getting that right, especially because the stoppers aren't that heavy. If it's heavier, you can feel it easier. But yeah, you want to let go when it's kind of beside you, and then you can add a little bit of extra force to direct it. But all right, this is more about International Space Station kind of context here.
A moon orbiting a planet, a spinning Ferris wheel, a yo-yo space station. They've all got at least one thing in common.
Find out how they all come full circle next on Real World.
A moon orbits a planet, just like a planet orbits a star, in a curved, nearly circular path. A Ferris wheel curves around a central point as well. And of course, when you go around the world with a yo-yo, it's circling around your hand.
And why does all this happen? Because of a little thing called centripetal force.
Basically, centripetal force is a force that makes an object, like planets or other satellites in space, follow a curved path. The word centripetal means center-seeking. What better place to study centripetal force than on the largest artificial satellite in space, the International Space Station? In addition to actually experiencing centripetal force, the freefall environment on board the ISS allows for some really cool demonstrations. So let's send it up to Expedition 22 astronaut Jeff Williams.
This is a tool. It's a special tool that we use on board the space station, actually during spacewalks. But it's a heavy metal object, and that's what I really wanted to use. And you can see I have it tied to a string, or with a string, onto this bungee right here. And it's just floating here in weightlessness. And you can see the string here is rather loose, and it's just kind of floating randomly. If I were to rotate this thing on the string around this bungee, and let me do this, you can see that the string pulls taut and stays tight. And the tool continues to rotate around the bungee. In fact, if you look really close at the bungee, you can see that the bungee bends at the point that it's rotating, and it bends toward the tool. And that is caused by the centripetal force due to the angular acceleration of the tool as it rotates around, keeping this string tight and keeping the rotation in a circular motion. It's the same kind of force that applies to the rotation of planets around the sun, or the moon around the Earth, or the space station around the Earth.
But you might notice that neither the moon nor the ISS is attached to Earth by a string, and they still orbit. Why is that? Well, think about this. Satellites would continue to move in a straight line because of inertia. Remember that inertia is the tendency of an object to keep on doing what it was doing before something forced it to change. Gravity is the force causing that change. Satellites in orbit around Earth are being pulled toward Earth by Earth's gravity. Acceleration occurs because gravity is continuously changing the satellite's direction. To understand how this works, take a look at this. I've got a yo-yo and I'm going to spin it around my finger on this table. The string here is acting like the force of gravity. If I let go when the yo-yo is at this top point, where do you think the yo-yo's inertia is going to take it? Will it continue in a circular motion? As you can see, the yo-yo wants to keep moving in a straight line instead of a curved one. That's inertia. The string is the only thing that held the yo-yo in its circular path. The string simulates gravity. In the same way, the ISS is held in orbit by Earth's gravity. If, for some strange reason, Earth's gravitational pull disappeared, the ISS would continue in whatever direction it was heading. Here's Jeff with another demonstration of centripetal force.
Okay, I've got this tea bag, and it's got tea in it, of course, and it's got air bubbles floating around here. The bubbles don't rise to the top in the absence of gravity in this weightless environment of the space station.
That's kind of an interesting thing. If you ever like carbonated beverages in a bottle that you can see, the bubbles float to the top because they're less dense than the liquid. But in space, density relies on gravity. So if they're less dense or more dense, doesn't matter. The bubbles are just like randomly in the liquid anywhere.
But if I were to rotate this, and let's see if I can rotate it and keep it in your view of the camera. Let's watch what happens. If you look really close, you'll see the air bubbles starting to coalesce in the center of the tea bag. I'm going to try one more time. There's the bubbles spread throughout the tea, and if I rotate it, the bubbles coalesce to the center of the tea and eventually form a circle. Why do they do that? Because of the centripetal force spread throughout the tea. The liquid tea goes to the outside of the bags and it forces the air into the center because the air has less mass, less density than the liquid. So the air goes to the center.
Centripetal forces affect things here on Earth, as well as in space. Things like Ferris wheels or the acceleration of a car going around a curve. But what other applications might this force have in space?
You've heard a lot of talk, perhaps, in regards to space exploration about artificial gravity. Perhaps you've seen some science fiction movies. For example, Star Trek, the TV show and the movies. They had gravity on board. They had some kind of a mysterious artificial gravity, make-believe, of course. But we've talked for years about artificial gravity on board a spacecraft, especially when you're going for a long period of time, for various reasons. One of the ways you could produce artificial gravity is by having a space station that rotates. Maybe very big, and the bigger it is, the slower the rotation would have to be to produce that centripetal force.
Jeff said that the bigger the station, the slower it would have to spin to create the centripetal force needed to make that artificial gravity. To find out why, we have to check out the math. Centripetal acceleration is equal to the velocity of the object squared, divided by the radius of the object. Spin is velocity divided by radius. The radius is the distance from the center of the circle to any point on the circle. The spin and size of the radius are actually in inverse proportion. On a spinning station, the larger the radius, the smaller the rate of change needed to simulate gravity.
Theoretically, you could do that. Theoretically, you could take a large station and produce, through centripetal force, sort of an artificial gravity to keep everything in its place. But the problem with that is when it's not very practical, because when you spin something and we turn our head around, our vestibular system will get a little bit messed up, and it's like if you're going around on a merry-go-round, riding a merry-go-round, then you step off the thing, or you spin around until you get dizzy. It'd be the same kind of thing. So I'm not sure artificial gravity in that way is very practical.
Wonder who will be the first to produce artificial gravity? But hey, don't just sit there and spin your wheels. Use that math to help solve this challenge. I'll see you next time on Real World.
Right, so with the tea bag, he was actually doing kind of what he said there at the end, creating an artificial gravity in the bag by spinning it. Because the more dense objects try to go straight, and so they move faster outward, and the less dense objects are pushed inward, not pushed inward, but they can't go past the things that are spinning outwards faster because of their greater density. And so he's basically creating a little gravitational field, so to speak, in the tea bag, which then makes the density of the bubbles separate. But instead of separating up, since it's constantly spinning, they just separate to the middle. So kind of an interesting thing. I think we'll call it a day there. To do the bowling ball demo, we need a little more time than we have left. So hope you guys have a good weekend if I don't see you tomorrow, and we'll see you again on Monday. You're welcome.